what I actually try to get to is kind of a certain general observation or principle in maybe homological algebra, but it sort of manifests itself when you try to study various homology theories with integral coefficients. But let me sort of approach this through a particular example, which is the most interesting for me, and that example being the drum homology characteristic P. But let me begin with a very quick reminder that characteristic zero. So you have some variety in characteristic zero, so over complex numbers, and you'll assume that it's smooth and projected.
Is that high enough for everyone to see?
Oh, what's the answer? Okay. So suppose you have some variety, let's say smooth projected. So okay, maybe you want to study its cohomology. And somehow Norton pointed out that at least if you care only about C coefficients, your cohomology of C coefficients, there is a way to do this purely algebraically. And one such way is to consider drum cohomology, which I'll just define to be the cohomology is a reductive of the algebraic drum lines. And yeah, let me point out that somehow this is a complex whose terms are vector bundles on X, but I completely neglect this structure. So I just use them as complexes of sheaves of vector spaces because the differential is really not linear because of the Leibniz rule. So this is just a complex of sheaves of CX. Oops. Okay, great. So it's a slightly funny object from the point of view of algebraic geometry, perhaps. And then, well, one of the foundational results about this is that this happens to have an additional structure, and in particular, there is a decomposition given by foot theory of that into just the direct sum of cohomology groups of sheaves of different properties. So somehow, for the purposes of computing global cohomology, this complex behaves as if there was no difference. Right, so of course, these are very different complexes, but their global cohomology turns out to be canonically the same. Okay, right. But it's about, so the way I stated it, it's an indication of two algebraic invariants attached to X. But the usual proof is really analytic. So you first of all go to the C infinity drum complex. Yeah, and you don't really work directly with that one. So I'll now go to characteristic P, and there I'll try to convince you that in some sense you can sort of study the analogous questions, but you can really do this just within the algebraic geometry because of some additional structures which you don't have in characteristic zero. So let me choose the prime number, and let me work with varieties over the field FP. And for now, let me just assume that they're smooth. So really global properties will not be so important for most of this. And I'll just work with the prime field parts and the data field convenience, but really you should feel free to replace this by any, at least by any perfect field of characteristic P. Okay. So I could just consider the same invariant. The drum homology, so which I'll define using the drum complex. So I'll just emphasize that this is now happening in characteristic P. That's confirmed. Okay, so it's still just a complex of sheaves of active vector spaces, but actually it has much more structure. So let me perform a slight modification to this complex. So let's recall that any such X in characteristic P carries a Frobenius isomorphism, which is just the identity on the underlying logical spaces of the scheme, and then you create the conflict between products. And let me just modify this complex by taking the push forward of all the terms along with Frobenius. Which is just to say that another way of saying this is that since the F really does nothing on the level of logical spaces, I just take the same sheaves of vector spaces, but I view them as modulus over functions in a different way. So, namely, functions now act through their P powers. And the claim is that now this complex is a complex of vector bundles. This is complex of vector bundles. Great. So the reason is that now I told you that I'm acting on forms by functions through P powers. So if I had some form omega, and if I had some function, I would multiply that form by its P power. And so if I were to apply a differential to that, of course, like as always by Leibniz rule, this would technically have two terms. But the first term would go away because we're having it has been front, so I'm allowed to move out these powers of functions from inside the differential. Okay. So magically, this is now really a complex of vector bundles, well, at the expense of modifying slightly the way it's linear structure in the terms. And this will be kind of the central object for me, so let me call this drx. And maybe just to get oriented, let me maybe say that, for instance, this sheaf is a vector bundle of rank equal to the degree of f, which is e to the power of n. So I've increased the ranks of these vector bundles by this Frobenius procedure, and now all these d's are maps of vector bundles. Okay, but if I care about global cohomology, this Frobenius operation made no harm because the global cohomology really only depends on the underlying FP, underlying sheaf of FP vector spaces. So the complex still computes what I want. Okay, right. But now let's try to kind of take the advantage of this additional linearity to study it perhaps more frequently. Okay. So if I have a complex and ultimately care about this global cohomology, I really only care about this complex up to quasi-isomorphism. So maybe the first thing to find out would be to figure out what are its cohomology objects. So what are these cohomology sheaves? And there is a very neat answer to this. So if I were to consider the cohomology sheaf of drx, that itself is an OX module because it's a complex of OX modules. And it turned out to be canonically isomorphic to the sheaf of forms. This is called the Cartier isomorphism. Right, but now there's no Frobenius put forward, so this is really the original sheaf of differential. Okay, so for example, if I is 0, then this is especially visible because then this H0 is just the kernel of the first differential. And I claim that, so this is supposed to be identified with just the starter sheaf when I is 0. And I claim that it's identified through sending functions to their P powers in this Frobenius bookmark. So clearly all of those are killed by the differential, and I claim that any function to the differential is locally P power. So this is an and there is an analogous explicit description of this as a isomorphism for larger. Okay. So I've got a complex of sheaves. I completely understand its cohomology sheaves, and I care about its quasi-isomorphism type. So, but still, just knowing cohomology sheaves doesn't tell me the whole quasi-isomorphism type, of course, because there might be many complexes with the same cohomology objects in the direct category and the Deligne category. So the kind of best, the kind of most naive hope would be that actually this is the most naive complex with such cohomology sheaves. So I could ask, is it true that the Rham complex is quasi-isomorphic to a complex with 0 different? Okay, where this is just my notation for a complex which has these sheaves as terms and no differentials. Okay, so to ask whether they are isomorphic is to ask whether the left and right hand side are isomorphic in the direct category of quasi-pure sheaves. So this method is sanity check that both complexes on the left and on the right, they have the same homology sheet, obviously. And if the answer to that was positive, then I would immediately get some kind of analog of Hodge decomposition, because I could just pass the global homology, and I would get that the Rham homology, which is the homology of the left-hand side, is decomposed as the direct sum of homology groups of the units. Right? Yeah, but this is provided that this works. Okay, so let me emphasize that already kind of the formulation of this question is specific to characteristic P, because well, characteristic 0, I could also ask if my Rham complex is kind of a direct sum of its homology sheaves, but this would only make sense in the category of sheaves of a complex of sheaves of C vector spaces, and this wouldn't have an analogous consequence even if that was true. So let me now move to saying whether the answer is actually yes, and so whether the answer will be more interesting than that always being true. But are there any questions before that?
Can I just ask about the isomorphism between the Rham cohomology and the cohomology of this complex?
Yeah.
Like, wouldn't this tell you that the global sections are isomorphic to the global sections pushed forward along the Frobenius? I mean,
right, but
think of vector space.
Yeah, that's a good sanity check. So let's check this on H0. So when I compute H0 of this whole dr of x, I'm not just computing H0 of the first term.
Yeah, right.
I should take the kernel of the differential.
Okay.
So I'm saying if I can take the global section.
Right. Thank you. I see. Thanks.
Yeah. Any other questions?
We're still only assuming smooth, no projectivity.
Right. Yeah. So it's rather funny that somehow that's a good point. So this will sometimes be true, even for non-proper varieties. Therefore, you would have this decomposition, which is I think essentially never true for non-proper varieties in characteristic theorem. Okay? And I mean, this is somehow right. Yeah. So that in fact, I've set up my notation so that it's to really obscure that's different, but really this decomposition shouldn't be thought of as the Hodge decomposition. It's rather some kind of other conjugate decomposition. And in particular, when we had a model over ZP, then even if the answer was yes, then that decomposition wouldn't really be there wouldn't really be an interpolation between that decomposition and the Hodge decomposition. Okay, yes, let me tell you what the answer is. So let's kind of approach this systematically. And so we're given this Rham complex, and we're asking whether it's what I'll call decomposable. So let me look at the smallest truncation of it, for which this is an interesting question. So let me truncate this in degrees at least 1, which to take it's some canonical procedure you can do to any complex in the abelian category. So this just means that it's a complex which maps to dr of x, and whose H0 and H1 are the same as for the Rham complex, but whose higher homology are 0. And so whenever I have a complex in any abelian category which just has homology in 2 degrees, its quite isomorphism type is completely controlled by a single class, which I'll call CX in this case, which is in a certain actor group from homology in larger degree to homology in the smaller degree. And one way to construct it is to view this as a genetic extension of degree 2 of omega 1 by all x. Okay, and this CX is characterized by the property that it's 0 if and only if that complex is decomposed. Okay, so great. So for any smooth variety characteristic P, I produced a completely canonical and inappropriate way, inappropriate sense class, which controls this first truncation. And so if the answer to that was yes, then this CX should better be 0. And it turns out that it's not always 0, and it's a repeatable theorem of Deligne and Illusie, which describes what this class actually is. So let me first of all rewrite this X space and more compactly. So it's the same as second cohomology of the dual to this bundle. Okay. So I've got a second cohomology class in the with division in the tangent bundle to my right. So it may be not so surprising that this is related to deformation theory. That's exactly the space where obstructions to deformations lie. And that's exactly what happens. So Cx is the obstruction I'll call it lifting x over d multi squared, which is just maybe jargon for saying that there exists a scheme x tilde over z multi squared, which I'll assume is flat over that. So it's really a kind of a genuine deformation whose special fiber is met. Yeah, so this is a deformation problem, and it's kind of a general fact that obstruction to solving applies in the script, and that obstruction is not always zero, and the claim is that it's actually equal to the obstruction to splitting that complex, even though a priori the complex is not obviously related to any kind of arithmetic quantity squared. Okay, but for kind of practical purposes, this is saying that if you manage to find the lifting, so let me assume that this still exists. Then you, in particular, get a decomposition of the truncation of the Rham complex in degrees 0 and 1. But actually, Deligne and Illusie extended this significantly further, namely to degrees up to p minus. By a rather kind of formal algebraic argument using the algorithm. And I'll say a bit more about it later. So if you truncate in degrees less than p, then actually the answer to that question is yes, provided this lift exists. And this is, well, this has immediate consequences for your growth homology, because sometimes the truncation is good enough for computing Rham. So again, if this still exists, then your Rham homology in degree n will be canonically isomorphic to some of the homology of the current forms, provided it's okay to compute n homologies in this truncation. So which happens precisely when n is less than p. And let me emphasize kind of in what sense this decomposition is canonical. So it's canonical in x tilde, which is to say that, or maybe I could say functional in x tilde. Which is to say that if you have a morphism between two varieties introduced to P, which was lifted to particular lifts over d multi squared, then the pullbacks on the left and right hand side will be matched by these induced decompositions. But in general, if you choose different lifts, you might get different decompositions. And this is a very important feature of them, which will sort of come about a little later. Okay. Great. So if you're willing to make this up, something that still exists, and if you care only about degrees less than p, then we basically were able to execute this strategy of getting some analogous Hodge decomposition. Okay, and what I'll talk for the rest of today is what happens if you still assume that the variety is liftable, which kind of seems to be a natural assumption, because there you seem to be seeing more structure than you would for a random variety. But you're looking at degrees p or larger. Okay, but before I go there, are there any questions?
You think C is slightly better than B, like not implied by B. If it were p minus 1, it would be implied, right?
Oh, I think it's literally implied, right?
Oh, okay.
It's a straight inequality, great.
But it could be a term from p minus 1 to p.
It could be a term from p minus 1 to p. Sorry.
Okay, so you just said stating C separately terms is.
Right, but I think it's also be a formal consequence, right?
Yeah.
Sorry, I see your point. But I think this first potential differential would come out of the group integrity. Yeah. Well, I can draw you a spectral sequence at the end. Maybe you'll end up being wrong. Okay. Sorry. Okay.
And what's true when you have a lift of Frobenius? There's something even stronger.
Right. So when you have a lift of Frobenius, and I'll say that, then you have a decomposition in all degrees. Right. And actually compatibility with certain additional algebra structure, which this was going to be one of my points. Yeah, sorry, I realized that I gave similar talks where people have been present before, but yeah, sure. Okay, yeah. So let me see what will happen in higher degrees. Yeah. So let me just make a disclosure that I don't know what's the answer to that question and for which class of varieties this decomposition exists. So the Deligne and Illusie tell us that being liftable over the monkey squared is a necessary condition, but it's definitely not sufficient. Let me put this in here. So there does exist X over FP, which you can even assume is smooth projection. And even liftable over ZP. So not just Z squared, such that part T fails if you go larger degrees. So, and by fails, I mean that really left and right hand side, they just have different dimensions of vector spaces. And this happens in degree E, which is the first degree version. Okay, could happen. Okay. So in particular, there's no way that the Rham complex is decomposable in all degrees. Or else that cohomology would imply that the vector spaces are replaceable. Okay, yeah, but I don't know where to expect kind of a concise answer as to what exactly is the class of varieties where the answer is yes. And I'd be very curious to know if there is a concise answer. Right. See, yeah, my goal will be to sort of, for the rest of the day, to say what you nonetheless can say about the whole Rham complex and where somehow this phenomenon comes from. Okay. But yeah, feel free to ask any questions today, right? Yeah, so yeah, again, like this question about decomposing the Rham complex is sort of it's interesting because it prompts us to look for what exactly are the additional structures present in the cohomology of varieties. And here's one such structure, which I mean, formally I will not use it, at least not explicitly, but I think it's really clarifying in organizing with what's going on here. So it's what's called a Sun operator. And I think it was discovered by Drinfeld. And then I think it was also perhaps independently was discovered by Bhatt and Lurie. And I think they were the ones who named it the Sun operator. So here's the structure. So suppose you have a scheme of monkey squared, which is a lift of some smooth varieties, say, then it induces the following additional structure on the Rham complex of that variety. So it's an endomorphism which we'll call theta x tilde, and it will really genuinely depend on x tilde. So it's actually in the Rham complex, but not as a genuine complex, but really as an object in direct category. And almost never, you're almost never able to actually represent this action as an endomorphism on the standard complex I wrote down. You almost, you have to replace it by some other models, but it was as a marker. And the key property of that operator is that it acts in a very simple way on cohomology. So theta x tilde is equal just to a multiple of the identity morphism on the item cohomology, which we already know to be just the different forms. So here you have a complex, you have an operator, and you know that its eigenvalues on various cohomology groups are just minus the degrees. So this minus is just a convention, if you like. If you were to behavior, this would immediately force your complex to be decomposable because it has different eigenvalues in different cohomology groups. But during characteristic P, and that statement about different eigenvalues no longer holds, because if you look at degree 0 or degree P, both eigenvalues there are 0 because P is equal to 0. So all it gives you is a generalized eigenspace decomposition. Which looks as follows. So dr of x decomposes according to the eigenvalues, and again, since we're in characteristic P, eigenvalues are just residues multiplied. So it would run over P possible elements, and I'll just note the pieces that dr x sub I, where this piece is characterized by the property that only the eigenvalue minus I appears there, just to say that this operator plus I is no more than this. Okay. But still, just having that structure forces you put your restriction on what kind of complex this can be. Because since I told you that what the eigenvalues and cohomology groups are, you can infer from this defining property what can be the cohomology sheaves of this I summon. So it has cohomology only in degrees where this minus I can appear, which are exactly degrees congruent to I1. So I plus P, I plus 2P, and so on. Okay. And this is just an non-trivial statement about the complex. I'm able to decompose it into P complexes such that for each of the summons, the cohomology is sort of staggered like this. And maybe especially concrete consequence is that if I were to truncate this complex in any P consecutive degrees, so starting with some degree and then ending in P degrees from there, that would actually be completely decomposable. Simply because by this property, each summand can contribute at most one cohomology object. Okay. So maybe I should say briefly what's the origin of the name. So this is alluding to the Sun operator in p-adic theory, which is something which you construct out of the Galois action on the cohomology of a variety over QP rather. And that, right. And so well, you could think of this as an integral refinement. So for instance, in the setting where this x tilde is actually lifted all the way to CP, you should think of this theta as of an integral refinement of the Sun operator coming from the Galois action on the generic. Okay, but really it's kind of the key, it's its subtle kind of integral property because this is all happening locally. Okay. Right, but the kind of elementary option is that it puts restrictions on what kind of complex this can be, and in particular, it recovers part B of Deligne and Illusie theorem by including A. Okay. Are there any questions about it? Right.
For A different from 0, this is not something you can get from Deligne and Illusie.
Right, not directly from Deligne and Illusie. There is a kind of I think there is a purely kind of algebraic way to prove this, but it kind of uses some homotopy algebra and it uses the special properties of the drum complex. Specifically, the Frobenius is 0 on forms starting from degree 1. But yeah, if you just had like a an algebra which, so yeah, if you were to axiomatize the drum complex in the most naive sense, this would be a formal consequence. Okay. Yeah, so let me tell you another structure which is present in the drum complex. And then I'll go into talking about where these examples come from. Yeah, I'm not quite sure what's the correct contribution for this other structure. So I think Margaret Blatt and Vadim Vologodsky had proof of this, but it's likely that any other perspective on the drum complex would kind of give a proof. So yeah, I'm happy to be corrected in this. So the statement is that if you have any symmetric variety in characteristic B, not necessarily liftable, then if you were to take its drum complex, and if you were to take its Frobenius pullback, it's a complex of X modules, so this makes sense. Then that is canonically decomposed. And well, the cohomology sheaves of that pullback are just pullbacks of the cohomology sheaves, because they're locally free sheaves. And if it's decomposable, then this is the only way it can be quasi-isomorphic to a complex with zero differential. And this decomposition is completely canonical, and it doesn't require a limit. So practically what I'm saying is that there are all these potential obstructions between different cohomology sheaves of the drum complex, but they'll die under Frobenius pullback. I mean, they're cohomology classes. So the brief could be said in one line somehow once you have the correct perspective on the drum complex. Let me not go into the details of the brief, but let me just say that this follows, for instance, once you realize that the drum, if you just look at the drum complex just as at the plane complex, I don't really know how to say this explicitly. You really have to choose a different model for the drum complex, which would be reflective of the fact that it actually has much more structure. And one way to kind of witness, one way to say what the structure is to look at the drum stack from properties of the drum stack. So it's a stack called X drum, which lives over X, and which recovers the drum complex as the cohomology of the structure sheet of that stack. Apply the modification to the direct forward of the structure. And then the decomposition follows from the fact that this stack, in a certain sense, becomes split after you pull back by the Frobenius, which means that there is a section of this form. And this is a stronger statement, but in fact, a much more elementary to prove because, for instance, it's a completely non-derived state. Right. But now, let me so let me draw kind of a practical consequence from this proposition, which again will not be necessarily strictly necessary, but this will sort of show kind of how various kind of properties of the variety affect whether its drum complex is expected to be decomposable or not. So the corollary here is that let's just put ourselves in a situation where, even though I said that a priori, so this is saying that pullback under Frobenius is supposed to kill all the obstructions to decompose into drum complex. Well, let's just put ourselves in a situation where there is no way that it kills anything. So let's suppose that X is Frobenius. This means that the canonical map operating the field power when X and Frobenius push forward has a section just as a map of X. So then I claim that the drum complex is split before taking the Frobenius. Okay. And this is rather formal from that general decomposition. So if I know the statement, so proof of the corollary. So the statement star can be basically rewritten as saying that, let me instead of pulling back along the Frobenius, let me just tensor my drum complex with the push forward of the structure field along the Frobenius. And this can just be recast as saying that this tensoring makes this into a decomposable complex. Again, those cohomology sheets have to be different than the product of the original cohomology sheets. This is true for any variety. But now, and there is also for any variety, there is an actual map from the drum complex into here, induced by the map from OX to the Frobenius push forward. But the point is that if I am Frobenius split, then there is a section of this map, just induced by the section on what I tensor with. So, without this section, this is a diagram which holds all the time. But if you have a section, then it means that you've established the drum complex as a direct summand of a decomposable complex. But then it forces the drum complex to be decomposable itself, basically, because you can combine the idempotents which cut out these direct summands with the idempotent which cuts out the R of X and say here, and you would be able to split the R of X. So therefore it's decomposed. Okay. So this was kind of a formal consequence under this assumption of this general kind of structure. Okay. Are there any questions with that?
So the implication is just projection form now?
Yeah, exactly. Or yeah, sorry. This is the cleanest way to say this. I was just saying that pulling back all over, yes. If you have a finite morphism, then thinking of sheaves on the total space is the same as thinking about modules over the push order structure sheaf under that marks. Yeah. So yeah, I should have just said projection form. Yeah. Great. So let me move to trying to discuss where these examples where drum cohomology is different from Hodge cohomology come from. And some of the approach which we'll take will be to really exploit another additional structure on the drum complex, which hasn't yet come up. And that structure will be modification. So I said that it's really not clear what's even the expected answer to the question of when the drum complex is decomposable. But this might be due to the fact that this question somehow ignores this additional algebra structure. And if you were to reintroduce this algebra structure into the question, it would have a very clean answer. Okay. So by algebra structure, I just mean that if I write my drum complex as I defined it, then this is a commutative DG algebra. Meaning that if I have some form in degree I and a form in degree j, I can multiply them to get a form in degree I plus j, and this is graded commutative. Now this is kind of a technicality at this point, but let me, since I really want to work in kind of direct category, I'll do everything up to quite as more. Let me back to a certain cruder notion of a commutative algebra, which is like what's some literal commutative algebra. So kind of if you don't exactly remember what this is, doesn't matter at all. They think of it as a complex plus some additional structure having to do with symmetric multiplication, with commutative multiplications. But I'll just write that this is packaged into a sequence of algebras together with certain maps between them. And each of these is an algebra in quasi-coherence. And it's a general piece of machinery that whenever you have a differential graded algebra in non-negative degrees, you get such a structure, but you can also, in this particular case, you can write it down explicitly, say using check complex for crystalline cohomology. And so really, this is the structure which I'll prefer to look at, basically because the fact that the Rham complex has a DG algebra structure, commutative DG algebra structure, is rather special to the Rham complex, whereas a cosimplicial commutative algebra structure arises from any reasonable homology construction in algebraic. Okay, so let me state what can be said about decomposition of the Rham complex if you now keep track of this algebra structure. So the Rham complex is quasi-isomorphic to the direct sum of differential forms together with the cosimplicial commutative algebra structure. So as cosimplicial commutative algebras. Which means that there has to be like a sequence of perhaps roofs where all variables are quasi-isomorphisms, where all the intermediate objects are not just complexes, but they're also themselves cosimplicial commutative algebras, and all the maps respect this multiplication structure. So this is true, if and only if there exists a lift x tilde over z must be squared of my variety. Together a lift of the convenience. So an endomorphism at tilde of this x tilde, which reduces to f1. Okay. So if I demand that there is such a decomposition compatible with this commutative algebra structure, then not only there has to be a lift, as the Deligne and Illusie theorem shows, but also there has to be a Frobenius lift, which is a rather stringent condition. Okay. So maybe it's worth remarking that, for instance, if your x is an abelian variety, then it always lifts just as a schema over z must be squared. But if Frobenius lifts, you're able to choose a lift such that the Frobenius lifts if and only if x is ordinary. Add the Frobenius lift over some lift of the variety. If and only if x is ordinary, which is to say that Frobenius pullback on the homologous obstruction sheet is an isomorphism. Okay, so it's a fairly stringent condition. Okay, and yeah, so the approach which I'll take is to then try to study decomposition of the Rham complex itself as a complex through this kind of more stringent properties. I'll try to decompose it together with the algebra structure, then fail in some way, and this will tell us something about the decomposition just as a complex. But before I go there, let me tell you the idea of the proof of this proposition, which will be instructive for what's to come. So the direction from right to left, so if you have a Frobenius lift, then the fact that the Rham complex decomposes, that's a theorem of Deligne and Illusie, and that's a key step in their proof of the theorem of homogeneity. So key step in Deligne and Illusie proof. Okay. But for me, most relevant will be the reverse direction, which says that it should be very hard to decompose it together with the algebra structure. But maybe before I explain the sketch of the argument, are there any questions about the basis for it? Especially if you're concerned about this derived commutative algebra business.
The left-hand side is the same as saying that you can split is the half stack.
Yes, exactly. Just to construct a section. And this will sort of be a splitting as algebras because you have a map of stacks that uses a map of algebras.
What is this direct sum thing as a cosimplicial commutative algebra?
Oh, let me give you a cheap answer, which is that it's a DG algebra in particular.
Yeah.
Like old content.
Okay. Well, but that would be.
So Dolkan, it's if you have it's dual to the simplicial Dolkan. Whenever I have a commutative DG algebra in degrees larger or equal to 0 cohomologically, I get a cosimplicial commutative algebra. Yeah, sorry, actually, this statement would also be true if you just ask that this is a quasi-isomorphism of commutative P geometers. That this would be kind of a weaker, maybe slightly boring statement. Great, so let me explain the Corbett charge. So this will not literally be the general brief, but let me rather give you an idea, which will kind of emphasize all that there is to know. So suppose I have such a decomposition. Then let me pass through cohomology. So first I get a decomposition in every degree. For that, I don't even need the algebra structure. But now the way the algebra structure enters is that now it forces the decomposition to be compatible with the Frobenius. So it's compatible with the Frobenius pullback, where it acts actually on the left and right hand side, because it's invariant at the right. So the reason is that, so this is because you can read off this Frobenius pullback on the drawn complex from some data which is intrinsic to this concept of commutative algebra structure, from the intrinsic Frobenius on this algebra. Mainly, this is all like thieves of commutative algebras in characteristic P, so they have their own Frobenius, and it happens to coincide with the Frobenius induced by the geometric morphism. But in particular, if you've got such a decomposition compatible with algebra structures, the induced thing on the cohomology has to be compatible with Frobenius. But I know that it's a very stringent condition, because remember that I told you that a lift induces such a decomposition in small degrees, but it's only functorial under maps which lift to that lift over Zima P squared. And you see that this is approaching having a lift of the Frobenius over Zima P squared. Whereas to actually prove that it forces, you have to just repeat this argument on the level of complexes rather than cohomology. But just to emphasize how this works, let me give an example. So suppose that X is a supersingular lift curve. And I told you that it shouldn't have a Frobenius lift. And indeed, Frobenius pullback on its first drawn cohomology, it's non-zero but nilpotent. Particularly, there is no way it decomposes. There is no way it decomposes as an operator in the direct sum of two one-dimensional vectors. And in fact, you can explicitly see that on Hodge cohomology that's actually zero. So this decomposition is not this. Yeah. And yeah, you sort of, this is the idea of the argument that you can recover the Frobenius from the algebra structure. Okay.
So sorry, so does this show that there exists a lift on every, a Frobenius lift on every lift of X?
No, quite the opposite. You get, it's an amusing fact that if there is a Frobenius lift on a single lift, then if you take any other lift, that wouldn't have a Frobenius lift. A lift that emails a variety. Yeah.
So does X, so do you have to require this lift to exist on the flat lift of X or on?
Oh, sorry, when I say every lift, I mean every flat lift. That's what
Okay. I see.
Because I don't want to do anything silly where I would just take X, view it as a schema of Zima P squared. That I can always do.
Of course. Yeah.
I mean, this has to do with the notion of a canonical lift of an ordinary Deligne right. It's characterized by the property that has a Frobenius. Okay, so let me use what we've learned here the remaining time to try to explain where these examples, where the drawn cohomology is different from Hodge cohomology come. So, I guess it's kind of a theme that I think maybe initiated by Sarah, or maybe just in general kind of functorial approach. So with the geometry is that if you're trying to show that some kind of nice behavior, that some pathology, if you like, appears on some variety, you should first try and prove that this pathology appears in some invariant context. So I'm trying to give an example of a variety where the drawn cohomology is different from Hodge cohomology, even though the variety is liftable. So let me first take a rather simple variety, say in the Deligne right. So for that, you can prove that actually, well, it's always liftable to Zeeman disparate in some way. And in fact, the Rham complex is always decomposed in all degrees. Right. But let me, so for, that isn't really an interesting example. But let me equivalent with group action, where this is just a discrete group, or possibly infinite. And let me assume that group action also lifts to Riemann disparate. So liftable over Riemann. It's systematic that the variety lifts, but it's in general not always true that the group action lifts. So if that's true, then again, if I just look at the Rham and Hodge cohomology together with this group action, nothing interesting really happens. I can't really discern between them, because this implies that if I take the Rham cohomology in any week, then it is isomorphic to the direct sum of Hodge cohomology. Oh, sorry, that should be compatible with the group action. So when n is smaller than b, this is an immediate consequence of Deligne and Illusie theorem. But the point is that the higher cohomology of the abelian variety is completely controlled by its first cohomology. This is just lambda n of h1. And so 1 is always less than b. So first cohomology is always covered by Deligne and Illusie theorem, but then higher cohomology you just get by a formal algebraic procedure. So it seems that nothing interesting is really happening. But I argue that something interesting will happen if you were to look not on the separate cohomology groups, but on the whole complex. So the key feature, which is responsible for examples where the Rham cohomology is different from Hodge, is that there exists a group action on the abelian variety, liftable even over Z2. But that if you were to compute the Rham cohomology of the stack motion, and I'll say in a second what I mean by this, of A by this group, then that would have smaller dimension than the dimension of the cohomology. So what do I mean by the cohomology of the stack? So let me just take as a definition this to be the equivariant cohomology of A with respect to G, which is just to say that I should take the cohomology in degree B of the group G, acting on the whole result of applying the derived functor of global sections to the Rham complex of A. So to the whole R gamma and Rham of A. And somehow analogously for cohomology of differential forms. Where here I view R gamma and Rham as an object of the direct category of representations. Like for instance, maybe you would choose some check cover which is stable under the group action, and you would use it to compute the cohomology, and then this would be like some potentially humongous complex of representations. Let me remark that this is only possible in view of that statement if this complex really contains more information than its cohomologies. So this is only possible if this whole complex is not otherwise isomorphic to the sum of single Rham cohomology groups and then would be group vector. If that was true, then this would have to be equality of dimensions, including for these isomorphisms.
I mean, not.
Yes, thanks. Right. So and this is slightly kind of maybe unfamiliar if you usually think about characteristic theorem, because in characteristic theorem, but last right hand side would always be invariantly isomorphic. For instance, by the application of Hodge theory. But it turns out that in characteristic P, they're not always the same. It really complex is more than its cohomology. So let me, in the remaining 3 minutes, let me state the key feature which allows you to have such an inequality. And let me just assert that even though this is kind of some funny stack, from this you can formally get an example of reduction right. So let me just focus on this. So the key kind of feature which we need to observe. So another proposition. Let's look at a very particular. So yeah, okay, first of all, let me say that to some extent, so the partially this decomposition is always true. So if you have any G acting on A, even not necessarily liftable, A and B line variety, then if you were to truncate this complex in degree below B, and that's the same, it's not a coincidence, it's the same bound as in Deligne and Illusie theorem. Now that would always be just a direct canonical as pure representation. This is an element where we prove this, for instance, using multiplication maps by various integers and by Deligne variety, using that they give different eigenvalues in different cohomology pairs. Multiplication by an integer. But now, more interestingly, let me just look at one particular example. So let me take some elliptic curve over F. And let me raise it to some large power. And so this is an n-dimensional Deligne variety. And let me make the group GL and Z act on it. It's because E was a group scheme, so I know how to add points and how to subtract them. So it makes sense to act by any mediums. And now let me M to be large now. Let me take M to be large now. So specifically, let me take M to be twice B. Maybe it's not quite optimal, but it has to be larger than B for sure. Then there is the following discrepancy between Rham and Hodge cohomology. So whatever your E is, the whole Rham cohomology is never a direct sum of its terms, just as representations. So in the direct category of this group. Whatever E is. So first, okay, this is why I have to, N has to be at least B for that to have a chance in the view of the person. But this is to be contrasted with the fact that if you were to consider cohomology of the structure sheet, which is kind of as good as Hodge cohomology because the Godant bundle is trivial, so cohomology of the structure sheet tells you everything about the whole Hodge cohomology in the case of an abelian variety. And that is sometimes quite isomorphic to the direct sum. Again, as a representation. But only if your elliptic curve was super singular. So if and only E is super singular. Which is to say that the Frobenius of E is 0 and 1H1. Okay. Since I ran out of time, let me just say the last sentence verbally. That so now by taking E to be a super singular elliptic curve and contrasting the behavior of the Rham and coherent, therefore Hodge cohomology, you get these examples by quotienting out this by an appropriate subgroup of GL and Z. But the whole concept is in proving these two statements. And so the idea is kind of provided by this consideration of the Rham complex together with the algebra structure. So the idea is you go and try to see if these decompositions actually hold compatible with the algebra structure. And it turns out that having a non-zero Frobenius is an obstruction to that. And then you somehow use that this group action is non-trivial enough to this obstruction persists, even if you just look at this as a complex of representations. And the point here is that in B, the Frobenius on the Rham cohomology is always non-zero, whether your elliptic curve is ordinary or super singular. But on the cohomology of the structure sheet, it's sometimes zero, but sometimes not. And so that's the key discrepancy. Sorry, this is rather big, but just for sure.
Thanks.
Can you say something about how do you pass from the non-splitting as an algebra to non-splitting as representation?
Great. So let me try to say it briefly, and if I don't succeed, then I can say this in person. So not everyone wait. So the point is that like what does algebra structure mean explicitly? Like if you have some A, which is maybe a simplicial commutative algebra. Then, well, in particular, maybe you were able to split it in small degrees. So maybe you have a map from H1 to your complex. Okay, so just a map of complexes. But then using multiplication in this A, you can get a map, say, from any derived symmetric power of this guy. Okay, using multiplication. Now, the point that this object itself really doesn't care about the algebra structure. So it might be like some complex in many degrees, but say the group action on it only depends on the group action on H1. But now you can ask whether this object splits as a sum of its cohomology. And this really, it's a potentially non-trivial question, but it doesn't care about the algebra structure because it's only a function of H1 as a model. But now it turns out that you can then relate obstructions to splitting A and obstructions to splitting that complex through this map. And well, this map really depends on the algebra structure. And that somehow, so Frobenius enters through this map because this map is related to Steenrod operations on classes coming from here. Pretty cool. Frobenius can get like right down into this slogan. So the slogan is that if you had a complex and you're able to put it to a derived commutative algebra structure with a particular, say, Frobenius on H1, then this forces something on what your complex might be as a complex.
Are you saying you can also characterize when the thing splits covariantly for Steenrod operations?
Right. I mean, this is sort of yeah. I mean, I think this is kind of asking that. It's perhaps probably like some weaker form of asking that it splits as an algebra.
Yeah.
Right. Oh, you mean like just as splits? I mean, for the drum complex, it's equivalent.
But actually, it's not weaker because the thing is not affine, and it's not clear that splitting an algebra would imply splitting over the Steenrod algebra.
Oh, sorry. I just maybe I think we're interpreting Steenrod operations somewhat different.
Okay.
Sorry, I was interpreting it in a way where it's sort of logically same, but yeah.
Okay.
But if you're talking about global cohomology, we can talk about it.
Things are abstract.
Sorry.
Right.
No. So when sorry for the naive question, but whenever there is a quasi-isomorphism then between Hodge and the Rham, do you get back the Cartier isomorphism on cohomology or?
Right. Yeah. So I mean, I could demand that my decomposition induces the Cartier isomorphism, but this would be an additional restriction. Because if it turned out to induce some other quasi-isomorphism, I can always twist by that on the side where it's all decomposable.
Thanks.
The abstract that reductive groups in positive characteristic doesn't vanish.
Right. So
hidden in this.
yeah, exactly. Sorry, I didn't get to that because I alluded too much fluff at the beginning. So the point is that you can so this action of GL and Z, it actually somehow you can kind of decompose it as a product of some Bochstein class and a class which comes from the cohomology of a group GLN and characteristic B. And this is what has to do with the fact that if you have a vector space and if you were to place it in cohomology to degree 1 and apply SP to that, then this would be a complex of representations of GLB, which is really not in general form.